Okay, and we're back again. So, as was suggested in the statement of the problem, I guess, I pulled up, excuse me, the Wikipedia page for, acoustic resonance, subheading Resonance of a Tube of Air, and found all of these useful diagrams and formulas that kind of halfway answered the question, but, man, I do not confidently know what to do with these to solve for a frequency. And if I know that I could come up with a frequency, but I wouldn't have any confidence that it was right. So I suggest we do two things. First of all, we take, so we have an open formula here, open cylinder, closed cylinder, formulas to solve for resonant frequency using the node number, or the mode number, I guess it'd be. V is the speed of sound, and then the length is L. The only difference here is we're using 2L for an open cylinder, 4L for a closed cylinder. So it would be pretty easy to come up with a frequency. Now, do it sanity checking that, knowing that it was right or wrong, or even in the ballpark. I don't know. So that's one tack we can take. What I think we should do is do some experimental verification and just get in the ballpark, do some sanity checking, and see, this actually does work, Okay, so let's do that. Let me show you what I got here. Let's get to, oh my God, let's get away from this computer. Yeah, computers, man, they're a passing fad. All right, so we're back to our scope. We've got SIG-Jenny kicking out, channel 2, which we see here. Ooh, variable frequency. We've got a counter, a meter set up as a counter here that'll track with that. And then, on channel 1, we have, well, let's go down here. Okay, we've got a pipe. Isn't that the truth? We've got you see another one off in the distance there in a messy garage. But, yeah, apologies for the mess. I didn't expect company. Just kidding. So, sorry for the disorienting pan here. But let me show you what we've got. Slide the tube away. What we've got is a speaker that I've drilled a hole through the magnet. That's where you see the yellow, black, and red coming out. And I've got a little electret microphone with a blocking cap, a current limiting resistor, or a power, I don't know, that was just the wiring diagram on the package. But I've got that poking through the speaker so that we can excite a frequency with the speaker and then measure its response with the microphone. And we've got the signal going to the speaker on one channel of the scope, bladow, and the picked up signal from the microphone going to the other channel of the scope. So this lets us in a sense, kind of ring the pipe and see which frequencies it likes to run at. Oh, I guess I moved that in. So we're just going to get that kind of in the neighborhood, not touching, so it doesn't rattle or anything. I happen to know that the 2-inch PVC we have here right now is 8 foot, for what it's worth. So we're just going to get a baseline, see if we can't verify what happens. Now, notice at the other end, the end is open. It does also bell mouth a little bit, so we're just going to disregard that, get some rough numbers. But what we'll find happens is as we crank up our amp here just a little bit, let's get both of these visible on screen. On screen. And as we sweep through frequency, so this line is the signal we're sending into the pipe. This fuzzy line is the signal we're getting back out. And we're going to find that there are some critical frequencies where, shapes start to emerge in the microphone signal. What we want to see, wow, actually that is something. What we want to see are frequencies where the overall amplitude of the microphone signal increases. Because we'll get up to, let me jump to some higher frequencies here and get just on channel 1. So you can see that signal all the way through. But you see it kind of gets crazy loud there. And it's not too perceptible to the ear, because the ear is kind of logarithmic. It can hear that something is 1/10 the volume, or 10 times the volume, or 100 times the volume. But when something doubles, maybe you can hear it's a little louder, maybe not, but it's not as dramatic as seeing it on screen. So that's the advantage of a scope, I think, is, yeah, there's another one. Yeah, 276. Okay, so now that we kind of see whatever a resonance is, we see what it looks like. So we're going to go back down to the low end of the spectrum. We're going to get both the channels on screen, and we're going to look for our first nice clean resonance. Now again, this is an 8-foot tube. Oh, there was something. So there we can see there is a nice clean something. It's not a sine wave. I mean, I don't know where the distortion comes in. Oh, that's it. Oh, I think I've got the volume up too high. Yeah, there we go. Okay. So now, having done that, we probably had some weird artifacts when we swept through the last time. So let's go back down to 0. Let's just look for any visible patterns. I'll tell you, before the first scope I had was an old big cabinet ICO. And it either wasn't triggered. Okay, there we go. Hey, look at that. That's pretty close to our target frequency. Our sample frequency, rather. So, maybe it's fair to assume that 8 feet is the magic number, but let's not go there yet. Let's just note these numbers down. Note these numbers in your workbook. Look around you. Look around you. I hope everybody gets the reference. If you haven't seen Look Around You, check it out. It's on YouTube. Funny. Yeah, okay, so we're getting a fair number of pretty sharp Q resonances. You know, you sweep 5 hertz one way, 5 hertz the other, and it goes away, and you hit it right in the center, and you see that nice, clean spike. Let's just run through for giggles and plot all of those that are visible, all of those that catch the naked eye. So let's call that 137. I'm not writing these down now, so my numbers might vary a little. Call that 206. That's a good one. 275. 344. 414. Yep, and that's the top end of the band. I think we got... Yeah, let's quit while we're ahead. Okay, we're back. So I did copy down the numbers that I got. See if those match what you have in your workbook at home, both of you. So we got 137, 207, 275, 344, 413. Blood ow! Oh, sorry, I don't know how that contrast works for you. So I dropped them in a spreadsheet just to do a quick and dirty graph to see how linear they were. So I don't know how well you can see, but I've got just those 5 values and then 1, 2, 3, 4, 5 just to give us an x-axis. Plotted them here, and what I was looking for is, you know, what are we catching here? Is this 1, 4, 5, 6, 7, and 8? Is this 1, 2, 5, 6, 9, 10? You know, we know that just from looking at these points at frequency 136, 137, frequency 207, we know that those are resonances. We don't know which numbers they are. So what I was curious is if the way that formula described it, and I have another copy of the formula right here, frequency equals the mode number, speed of sound, 2L. I don't know if you can read that. This is Everest again. This is a pretty handy book. They've got a very similar explanation here. So the way that formula described it seemed to be that the resonance number was just a multiple. It was a linear relationship. And sure as shit, what we see is we get a perfectly straight line connecting these. That's the significant part, not the slope of the line, anything else. These things are arbitrary. And the data between these points doesn't exist at all. It's really just we have a resonance here, a resonance here, a resonance here, a resonance here, resonance here. We could figure out the relative magnitudes of those or note the phase, that this one's in phase, this one's out of phase. We're not going to get into that. That's just craziness. So let's assume that 137 is the lowest allowable open tube resonance. I kind of want to drill down just on open tubes because, I do not remember what I did. That's been 3 years or so, but I am pretty sure that I left the end of the tube open. We can play some more with closed tube resonance, and I did a little bit before we turned on the camera, and it does not seem as predictable. The equation would make you think that it's just different values. It's a multiple of 4 instead of a multiple of 2, or it's a quarter instead of a half. That's not what I got. The behavior seemed really unpredictable when I closed the end of the tube. So we won't get into that yet. We'll keep our powder dry, but maybe that's a show for another day. Anyway, sorry to have you staring at the computer so long there. I certainly hate doing that, so I don't know why I subject you to it. Okay, so we know they're linear. Let's regroup a little bit. I guess we should get back to doing the math, as we said, but that's the part that I don't have much of a talent for. And we're back. Hello, everybody. Okay, so I just filled out a little table here. So we're dealing with an 8 foot by 2 inch diameter tube, resonances by order predicted from this guy, which we're told is the formula for an open tube resonance by order number. So here I've got order number on the left, predicted frequency on the right, and what the formula gives us is that the first order, whatever that means, should be 70.6 hertz. Second order, 141.3. Third order, 211.9. I'm rounding, you know how it is. 282.5. 353.1. Here's our predicted numbers. Now let me cut here and plot them both on a chart and see how they line up. Okay, and we're back. Sorry for the shitty camera work. So, I don't know how well you can see there. I should stop, probably try to show things to the camera I can't show. But we've got our measured and predicted values plotted here by order number. Now, this blue point right here is the first one that we measured. But just because of how nicely those line up, I'm going to assume that we're missing the first order and that we actually got the second order, which would be convenient because that would give us an answer that we were looking for. Second order harmonic, whatever the shit that is, does not matter, I suppose. So, I guess I need to decide if this is a family show before I swear too much more. Nah, we'll cut it out in post. So, we're predicting, let's see, this is probably a more visible table. We're predicting that there is actually a first order harmonic, if such a thing exists, at 70.6 hertz. Our formula tells us that this number, n, can be any integer greater than 0, equal to or greater than 0. So that makes me think that there must be such a thing as a first harmonic in some circumstance, open or closed tube or something or other. So let's see if we can't find one. I'm going to stand up. Why not? Why not? Sorry for the jerky camera. Yeah, I gotta work on that, I guess. Get to frequency there. Okay. So, are we hearing anything? Okay, are we seeing anything? So really, we're just looking to see what happens at 70. Yeah, that could be something. Huh. Now that's interesting because it looks like we're seeing a peak come up here and come up here. And if that's the case, the separation is, what is that? About 2, 4, 6 milliseconds. But the inducing frequency is a lot less than that. Slower. I mean, yeah, I don't get that. But let's see what happens as we... Yeah, and see, now we're back to almost no response by 70, so there's definitely something that happens right in there, but I don't know what it is. Let's see what... Huh. It almost seems... Oh, shit, look at that. 45. 45 is a multiple of 70, and I see a little something there. You know, you may not believe me, but there's something very convincing when you're twiddling a knob. And you can see it. Oh, yeah, that's pretty compelling, I think. Oh, and we got something there. Man, how did we miss all these? 91.5. There's a little something there. 114. And then we get our nice, our 136. And we go up from there. So I guess, yeah, I don't quite know what to read into that, but I'm tired of doing this. This is an 8-foot tube, 2 inches. We could also verify that an 1.5-inch PVC tube resonates at the same frequency because we think it's only length. It's a factor, not diameter. We could do that. We could do all this and more, but we won't because I'm done with it. So I think we're just going to say that we have found a length of 2-foot pipe that has a second-order harmonic, which now I think we understand a little better what that means, at the frequency that we heard in that clip, which turned out to be 230, what was it? No, 238, something like that. But I think we can say it's 8 foot plus or minus a couple inches. Yeah, I think that's a very reasonable answer. So, the only thing that remains now is to, let's do the wrap-up. So, I don't know. Did we do it? I think we did it. Fun with feedback, redux. What did we find? We measured our sample. We're fairly confident that the tone we were hearing was almost exactly 139 hertz. I feel good about that now. Not 110. That first one was way off, wasn't it? The second order harmonic thing, but we did find a formula that had a place for an order number. Order number sounds like Amazon. There was a field, that N number. Oh shit, I didn't write the formula. You saw it. You guys playing it the home game. I'm probably stoned anyway. Where was I going with that? Okay, so we found some mechanism to account for what the hell I meant by this. It's the second order harmonic. Well, I don't exactly have a sense what that means in practice, but the math worked out pretty tidy with what we measured. So, with our table, with our graph, all that, we found that the loudest and most perceptible harmonic, resonant frequency, seemed to be called the second order, according to the formula. So, second order harmonic for an open tube, we found that the resonant... I don't know if I'm in the shot or not. I guess it doesn't matter, actually. My hands are. The resonant frequency was 2 times the speed of sound. 11... Oh, that's wrong. Well, okay, we're still close. That should be 2260. Speed of sound in air is 1130 feet per second. But, not off by a factor of 10 or anything. So, 2230 divided by 2L, we know that the resonant frequency we're looking for is 139. So 139 equals 2230 divided by, again, this should be a 60. Let's just, you know what? Let's not fuck around anymore. We want this celebration to mean something when we're said and done. So we'll make that a 6, and we'll make that a 6. So we get 2260. Now I know how to do the math. Divided by 139, I believe, will give us 16.25, which is 2L. So divide by 2, I get 8.12. Ha! That was easy. It doesn't even look like a 1. But you see where I'm going with this, right? Yeah. 8.12. What is that, about an eighth of a foot? Whatever the hell an eighth of a foot is. Okay, so I think that we have our answer, disregarding end effects and everything. 8.12, the magic number. So there you have it. Wasn't that fun? With feedback? Alright. The only thing left to do is to party. Fuck. I don't even care anymore. Taking us out with the thermals from More Parts Per Million. Badass album. I don't know if you guys are into the thermals, but maybe it's their second studio album. It might be 40 minutes cover to cover. This is how it wraps up. And this is how we wrap up. Thanks for joining us. Stay tuned for another occasional Radcast at some point in the future. Maybe coming soon, maybe not coming soon. See you next time.